Welcome to our lecture on NMR, Nuclear Magnetic Resonance, NMR. So nuclear magnetic resonance spectroscopy is the most powerful tool for organic structure determination, and I would agree with this. We'll be talking about proton and carbon NMR, but mostly I want you to be able to read and assign proton NMR structure, peaks, spectrum, spectra with structure. If you're going to study organic chemistry, then NMR is going to be a very important tool for you to determine your structure, and that's called compound characterization. There are about 4 things that NMR can teach you, and so I want you to be able to get about 4 things from a proton NMR spectra. So quickly, just going through the theory of how this works, you can also just become an NMR specialist, but the nucleus has to have an odd atomic number. So that's why proton spectra work. Carbon we have to look at the carbon 13 for the odd number. And what happens is this, we spin, so when you put your compound in the NMR tube, it spins. Okay, so it'll spin very quickly, and then because it's odd, it has a charge, and then it creates a magnetic moment, because then you put it in a strong magnet. And then, so when you put this spinning, it's a little magnet. So when you put this little magnet, which is your compound with the 1 proton, and you're spinning it, and it's creating this magnetic field, and then you put it in a larger magnetic field, then you can create a spectrum. So what happens is it orientates, so you'll hit this with a pulse. It's called a pulse when you hit it with an externally applied field, and you're hitting it with NMR waves, and NMR are radio waves. Okay, so they're very large, low energy waves, radio waves, and they hit these nuclei and they turn them over. Okay, so that's how the whole spin originally gets aligned, and then you take it away, you withdraw the pulse, and then they resonate down to their lower energy. And so that's what's happening here when you pull the pulse away. And then this difference in energy gap can be captured on an NMR spectra. And so there is some math, but we don't have to learn the math. I just want you to be able to apply the spectra identification for the compounds. So if you did want to go on to higher level NMR, you might need to study the math associated. So like I said, there's 2 different energy states. It's this energy difference that we're going to capture in the spectra. And that's what it's showing you, how this energy, lots of physics here. Now, shielded protons, we're going to find that shielded protons will protect the nuclei from the magnetic field. The BO is the magnetic field from the instrument. Okay, and shielded protons are going to be shielded based on other elements in the structure. So here they're showing you that these are more shielded, so they're at higher field, and then this OH, because its dipole moment, is less shielded because you're pulling those electrons away. So if you pull the electrons away, and this little hydrogen here doesn't have electrons, no electrons really, they've been pulled away, they can't be shielded. Okay, so it's going to be a lower field. And the lower field, it's always been reversed. I can't stand the higher lower thing. basically this OH will probably show up around 4 ppm. You see how that's a higher number than this one here, which will show up around, let's see, 1, 2, 3, maybe 2.5 ppm. ppm is parts per million, and that is the units. So you need to know the units. So we say that a proton is deshielded somewhat by the presence of the electronegative oxygen atom. So the oxygen is pulling the electrons, and that deshields it from you're deshielding it from the magnet. Okay, so I want you to understand 4 things about the NMR signal. You can, 1, so this is an important slide, the different kinds of protons present. So we're going to look at structure, and we're going to ask ourselves, how many NMR peaks? Okay, and so if you have something like this compound here, and you're going to learn this has only 1 NMR peak. How many hydrogens? It has 6 hydrogens. Okay, so 1 NMR peak, because each one of these hydrogens is in the same environment. So it's the same kind of proton. It's in the same environment. It's attached to the same things, okay? So you only see 1 peak, okay? So that's one thing you need. The location of the signal shows how shielded or deshielded. Well, this benzene ring will deshield it. So this hydrogen here, you'll see, okay, so this will be 6 hydrogens. It'll be around 7.2 ppm. And that's with the location. So the ppm tells you that this is aromatic. These are aromatic protons, that they're benzene protons. The intensity shows the number of protons. So this area underneath the curve, which will be Fourier Transform, you'll see an integral. It's going to integrate out to 6 hydrogens. So the area under the curve is going to represent 6 hydrogens. So that's how you know what the intensity is. And the splitting shows the number of protons adjacent. This is the n+1 rule. So this is the important slide here, that you need to be able to do these 4 things when you're looking at NMR spectra. This is the NMR spectrometer. Like if you're going to do spectroscopy, you're going to do some research, you will end up putting your compound in the sample tube, you'll put it in the big magnet, you will turn on the pulsing, and then in about 10 minutes, maybe less than that, you'll get your nice printout of your spectra. And it's something like this. So you'll have an NMR room. I would suggest that you put all your phones and anything magnetic not close to this 400 megahertz NMR. All right, so when you get a graph here, so here's an NMR graph. You should see here that you have two types of hydrogens. Okay, so you have these 3 here, and it's going to show up at this, and then you have this 1 hydrogen that's deshielded, and so it's lower field, which is going to be a higher ppm. Okay, Tetramethylsilane, TMS, is usually added as an internal standard, and it shows up at 0 ppm, and that's because it basically does not absorb at all, because it's not shielded, because silica is less electronegative than carbon. Okay, so I have had to use this math before, because if you use like a 650 megahertz NMR, then you're going to have to do this math to show what your chemical shift would be. So, but you won't have to do that unless you're publishing. All right, so, and that's what they're showing you here. I'm not going to worry about that. what you do need to know, and you can refer to these, is the NMR chart. So if you have an electronegative atom, so you're looking at these hydrogens connected to like a fluorine, these hydrogens are going to show up at 4.3 ppm, and the delta means that's a delta, and it means the shift, and it's going to be ppm, and this is very electronegative. So iodide is less electronegative, so if this was iodide, then this would show up at 2.2 ppm. The OH here is at, so that would have been at 3. So if you have that as an OH, this hydrogen here would show up at 3.4 ppm. So the more electronegative atom deshields and gives you a larger shift value. So additional electronegative atoms would cause an increase in chemical shift. So the chemical shift, the ppm, tells you about your electronegative atom. So if you increase the electronegativity of the atom that's connected to the carbon, then your hydrogen is going to have a larger ppm value. It's going to show up at a larger ppm value. So here, these butane, essentially the carbons are connected to carbons. There's no electronegative atom. So they're all at 0.9, 1.1, 1.3, okay? Here you have the bromine here, so you can see this is 0.9, 1.1. Now you see a little bit of shift here because you're getting, this is feeling a little bit of the deshielding from the bromine. It's 3 bonds away, 1, 2, 3. 3 bonds is about as far as you can go. Here, this is 2 bonds, so it really fills it at 3.4. So this helps you tell a little bit about your functional group. You can see that if you have a CH on an alkyne, terminal alkyne, you're going to show that at 2.5. If you have a CH on an sp2, that shows up even more, 5.6 or 5 to 6. Here, if you have a halogen or oxygen, it's between 3 and 4. The aromatic is 7.2. So these are those hydrogens here. Those are 7.2. Benzylic is going to show up. So that hydrogen would show up about 2.3. Aldehyde, look at aldehyde here. It's all the way to 9 to 10. Okay, this is significant because nothing else shows up here. So that right there can tell you whether you have an aldehyde. Carboxylic acid, it's going to show up between 10 and 11. Okay. Alcohol, these OHs, since they're acidic, are going to be variable. So that's why you see variable. You can't really rely on them to integrate properly, and you can't rely on them to show up at the same ppm always, okay, because they're going to be exchanging with the environment because they're acidic. And this is just showing you why the benzene, the aromatic hydrogens, are all the way up around 7 ppm, 7 to 8 ppm here. And the reason why is because the electrons that are going above and below the ring are creating their own magnetic field. And that magnetic field opposes the external magnetic field. Also, alkenes do the same thing. You have pi bonds. So whenever you have pi bonds, those electrons will generate their own magnetic field. And that's why if you have an alkene proton, which is really unique, to see something around 5 or 6 ppm. Alkynes, they also have pi bonds, so they generate an electric field above and below the pi bonds, and that's why you can see that all the way at a 2.5, even though carbon is not bromine, right? So or oxygen. It's not very electronegative, but that hydrogen will experience its own deshielding. Aldehyde proton has, because of the carbonyl, and that resonance will show up all the way at 9 to 10. Okay, so the acidic protons depend on concentration. The signal can be anywhere from 3.5 to 4.5, but the peaks exchange, so the integration is not always going to be correct, and it's going to be variable. All right, so this is a carboxylic acid. Because the high polarity of the carboxylic acid, your acidic proton can shift greater than 10. So you can see this offset at 2.0 means it's probably around 12 ppm. Once again, usually you set your scale from 0 to 10 ppm. Okay, so the 4 things I need you to be able to do. One of them is the number of signals, okay? So when you see this, you're like, okay, these are unique, and these are all connected to the same thing. They experience the same thing. So there's 2 unique signals. And then you got to be able to say, where would what ppm? What's the chemical shift? And these carbons are connected to those carbons, so I'm going to say it's 0.9 ppm. Okay, so it's about 1.3 ppm. So that's a similar area, 1.3 ppm. And then this carbon, hydrogen here, is connected to an oxygen, and so here it is at 3.2 ppm. And then the integration, which is not shown here under the curve, would tell you that this is 3 hydrogens, and the area under here, when you had an NMR integration, would integrate out to be 9 hydrogens. And then our n+1 rule is the last thing I'll teach you. How many signals here? Well, A, this is A. Those will all be the same. These would be the same. There's C. And then this is B. So 3 signals. Okay, predict the chemical shifts of the protons in the following compounds. Okay, so how many? Let's do number of peaks. First one you would see 2. What about here? This would be 1, 2, 3. So you'd see 3. And here, sometimes you might have to draw these Lewis structures out. So you can see where these are different, this is different, and then these would be different. So this would be 3 peaks. Predict the shifts. Okay, well, we said the OA should probably be around 12 ppm. And this carbon next to a carbonyl, you'd have to look at a sheet. Experimental value is 2.1 ppm. So you should be able to pick the shifts and the number of peaks. This carbon next to the chlorine, between 3 and 4, it's showing up at 3.7 ppm. This carbon here in between, it's probably not going to be anything exciting, 1.7 ppm. And then this CH3 is probably going to be about 1.3 ppm or 0.9 ppm. Okay, here, these are going to be like at 0.9 ppm. Now we have the vinyl here. This is going to be between, these are going to be between 5 and 6 ppm. And so it says the B protons and C are between 5 and 6 experimentally. This is 5.8 ppm, and this is 4.9 ppm, because those are sp2 carbon hydrogens. Okay, so intensity of signals. This is the numbers. So when the number of protons, hydrogens present. So here you have 3. And so if you were out to get a, sometimes you get the computer and you set the value to 1 and then it'll integrate to whole numbers nearly. Sometimes you get them where you get just the millimeters high, and you would get a ruler, and then you would say, okay, you would say, well, this peak here corresponds to this with 3 hydrogens, so you would say 11.5, get out your calculator, divide by 3. That gives me 3.8 millimeters for 1 hydrogen. And so then here, if this is 34.0 millimeters, then you would do 34 divided by 3.8, and then you'd say, okay, that's 8.95. That rounds up to 9 hydrogens, and you see 3, 3, and 3, so that's 9 hydrogens. So the integral height, you figure out what the height is for 1 hydrogen, and then you can figure out the number of hydrogens present. So the intensity of the signal, the integration, should tell you how many hydrogens you have. And I always check that. I check the number of signals, I check where the chemical shift should be, I count up how many hydrogens are present, and then I do this thing called n+1 rule. And that's what this is. This spin, splitting. This is your n+1 rule. It's your neighbors. And what happens is when your neighbor hydrogen, okay, so what happens here? We'll just look at something like this. Okay, so this is this carbon here has a neighbor carbon. So this is this neighbor carbon. And this hydrogen here will split this hydrogen here. Okay, so it'll split these hydrogens. And so how many neighbors does the black hydrogen have? It has 2 hydrogen neighbors. So the black hydrogen has 2 yellow hydrogen neighbors. Okay, so this rule by Pascal is called your neighbor plus 1 rule. And so if he has 2 neighbors, what's 2 plus 1? 3. So what you're actually going to see is a peak for the black hydrogens that look like a triplet. So the area under the curve, so you'll see the integration under the curve for the black hydrogens would be 3 hydrogens, but it's a triplet. And this triplet, and you actually call it a triplet, just write a T, means that the neighboring carbon has 2 hydrogens. Now, what would the yellow hydrogens be? Well, the yellow hydrogens has 3 black hydrogen neighbors, right? So what's n+1? 3 plus 1 is 4. So this is a quartet. So you would see the yellow hydrogens in its peak would look like this. 1, 2, 3, 4. And that area under the curve would correlate to 2 hydrogens, but you would see a quartet. And that's because the neighbors are acting like little magnets, and they're causing these peaks to split. And so this is what you're seeing here. So when you see this doublet, this is a doublet, and then this is a triplet. So the first thing, you have 2 distinct hydrogens, 2 different environments. So you see that here. And you have this, the B hydrogens here are only connected to a carbon with 1 bromine. So they're showing up around 4, with 2, so they're showing up at 4. I'm sorry, they only have one bromine, so they're showing up at 4. And then this hydrogen here has a carbon connected to 2 bromine, and it's showing up at a lower field or a higher ppm. And now, the thing is though, these neighbors here, the red hydrogen has how many green hydrogen neighbors? the green hydrogen, it has 1, right? 1 green hydrogen. So what's the n plus 1? 1 plus 1 is 2. That's a doublet, okay? So the doublet belongs to the red hydrogens. The 2 red hydrogens is the doublet because its neighbor only has 1 and it's splitting it. Just like the green hydrogen here is 1 hydrogen and it has 2 red hydrogen neighbors, right? So what's n plus 1? 2 plus 1 is 3. So that's why it's a triplet. So it's a triplet because it has 2 red hydrogen neighbors. And so this is showing you how and why it does the splitting. So one of these is causing, one of these fills this opposing field and it will show up a peak at a higher number, whereas the other one will show up at a lower number. And that's why you get a doublet. And it's all the effect from the green hydrogen here, the neighbor. And so here, this one, the red hydrogen is going to fill both neighbors. It's going to fill this neighbor here, and it's going to give a peak, and then they're going to cancel each other out here, and it's going to show up here, and then you're going to get a lower field here, and that gives you a triplet. This is actually called Pascal's rule, the n plus 1, and this is Pascal's triangle. And so this is mathematics applied to NMR. But anyway, so you can see you get lots of different quartets, quintets, sextets, heptets. So now the disting, protons normally next to each other, right next to each other will split each other. Those are the neighbors. Sometimes protons bonded on the same carbon can split each other if they're not equivalent. We call those diastereotopic. Protons separated by 4 or more bonds will not split each other. So it's usually around 3 bonds or less. And so this thing called long-range coupling, you can actually calculate the hertz between these two, and they're called J constants. And the unit is hertz. And if they're related to each other, then you can say they have the same J constants and they are related to each other. We don't go into the J constants here. That's probably more of a graduate level, upper grad. I just want you to be able to do the 4 things. I want you to be able to look at this spectra here and say, okay, we're going to have we're going to have 3 peaks, spectra peaks, because we've got NMR peaks. And we're going to be able to say that this is going to be the higher field at 1.3 ppm because of its not very electronegative environment. Then you could look at this and say, oh, this is benzylic, so it's going to be around 2.3 ppm. And then I want you to be able to look at these and say, oh, these are aromatic, so they're going to be between about 7.5 ppm. So I want you to be able to tell me how many peaks there are. That's one thing. Remember, there's 4 things. The second thing, I want you to be able to tell me what's the chemical shift based on the electrochemical environment. And then here, I want you to know that the integration 3, 2, 5, and be able to count. So integration, what does it mean? It means the number of hydrogens in the molecule. That should be accounted for. And then the 4th thing is the n plus 1 rule. So the splitting, we call that the splitting. So you see that this red hydrogen, this red one here, its neighbors have 2 hydrogens. So what's 2 plus 1? 3. So we're thinking triplet. Is that a triplet? Yes, that's a triplet. You go to the blue hydrogens here, and what's its neighbor? Its neighbor has 3. This neighbor doesn't have any, okay? So what's 3 plus 1? That's 4, quartet. Do you see that that's 4? That's your quartet. And then you go to the green here, and what are these? These a lot of times you'll report as a multiplet, okay, because they're all kind of together, and this would be a doublet, and this would be a triplet, and the overlap. So a lot of times that's just considered a multiplet. Okay, so the leaning of a multiplet is characteristic of an ethyl group. So an ethyl group is this. Okay, so here you have this one here is a quartet, and this one would be a triplet. Okay, so this would be the triplet here, and then this would be the quartet. Okay, so isopropyl groups here. So you have 1, 2, 3 peaks. You should have 3 NMR peaks. This one, A is going to be a singlet, and it's going to show up around 2 ppm. You should be able to look at this like this. The C is 3 plus 3 is 6. So what's 6 plus 1? 7. So that's a septet. And that's going to show up probably around 2 ppm. And then you have these here, the B, and they're going to be a doublet. And they're going to show up at maybe 1.3 ppm. So they're in the least electronegative environment, so you're going to see those here. And you see that's about 1.3 ppm, and that's B. And there's 6 protons there, and it's showing you it's expanded here as a doublet. Is it a doublet? It should be a doublet, yes. Okay, you come here to C. C is right here. It's only 1 proton, and it's a septet. And it looks like a septet, doesn't it? And then you have A, and A is a singlet, 3 protons, and it's around 2 ppm. Okay, so, and that's the solved one we just did. You can go through these. I'm not going to talk about coupling constants. You can read about it. The values for the coupling constant, they're just showing you that you can tell whether you have a cis or trans, because these hydrogens are going to be, the coupling constants is the distance between these peaks are going to be larger than, let's say you have a cis alkene, they're going to be less, they'll be closer. So these coupling constants can tell you a lot about whether something's geminal, cis, trans, what kind of proton environment. Okay, proton NMR for toluene, you can look at that. This is showing you the coupling constants between cis and trans. And you can read more about coupling constants. I find it fascinating and interesting. And you can do this splitting tree for styrene. I'm not going to require you to do that. Remember, I just want you to be able to do the 4 things of a spectrum. So here's styrene. We'll go over that. Non-equivalence. You'll probably run into that 1 or 2 examples, and that's if you have a stereo isomer, stereochemical, diastereotopic proton. It sees a different environment and different conformations of the compound, and you'll see that sometimes you get an extra splitting. You can also, these diastereotopic protons, what they're called, will also give you matching J splitting constants, and then you know that they are related to each other. And I'm not going to talk about the diastereotopic protons. Time dependence NMR, you can do different timing. This is showing you that if your sample is pure and concentrated, you can see splitting patterns that you wouldn't normally see. And they're showing you the difference between a pure sample and impure sample. We used to say at Eli Lilly, if you put trash in, you get trash out. That means you need to purify your compound, you need to drive your reaction to completion and get a good NMR spectra. They're showing you that the NH is broad here because it's got an exchange rate, meaning it's an acidic proton. So you can't always depend on it, and they're going to be like little broad peaks. And so you can do a deuterium shake. This is a thing you can do in the lab with D2O, and then you can make that peak disappear because it'll exchange out with D2O. You just put a little D2O and shake it up, and then you take the NMR spectra, and then you won't see that peak at all. Now carbon NMR. So we're just going to touch on carbon NMR, and then we're going to be done with NMR. The carbon-13 is the odd mass, so it's the one that has the magnetic spin. Carbon-12 does not. So this is a carbon-13 NMR, and they're showing you that the nuclei, how they get the spectra. These are your scale is going to be a little bit different. You see it's from 0 to 200, but it's still going to be very similar. You have alkanes at the low field, alkyl halides, alkynes, alcohols, because they're more electronegative in this area. You have alkenes and aromatic around this area, like 120 ppm, and then the carbonyl is around 200. So you can find the carbonyl. Remember, we're looking for carbon now, and a lot of times the carbonyl peaks take a long time to show up. Carbon NMR takes a long time. A lot of times people will get to sign up for the NMR Spectra overnight if they want a carbon, or you got to load like a lot of maybe 20 to 30 milligrams of sample to get a carbon NMR, because carbon-13 is not everywhere. It's like, what, 1.1% abundance, as opposed to hydrogen-1 is like, what, 90-some abundance? Okay, so here you have the a lot of times you do to compare. So this is NMR Proton NMR down here, and then this is your carbon spectra up here, and you can see the difference in the scale here. Here at 180 you have the carbonyl. Okay, so you have the carbonyl. Remember, this is carbon here. This is your solvent, it's chloroform, and then you get in this area, and this is your aromatic for carbon. And you see that that's those 4 carbons here. So you have actually, and there's your 4 carbons, right? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So there's 5 carbons. So can you account for your carbons, and can you assign based on spectra? Down below, your hydrogens here, these are all aromatic. So you're going to see them around the 7. This aldehyde peak at 9.4 is this one here. And then you also have this peak here. It's probably your NH peak. The difference between proton and carbon is the frequency length is different, right? That's why you have 0 to 200 ppm spectra scale for carbon, and you have basically a 0 to 12 ppm for a proton. The spin-spin splitting is unlikely that a carbon would be adjacent to another carbon, so the spinning is negligible. You have to do a longer, a lot of times we do different kinds of carbon spectra. And this is just an example. And you can decouple the carbon. There's like 4 different carbon techniques. I have my own favorite, where it puts the odd number of carbons above, and then below you have the even. And the important interpreter in NMR, just do you know the number of signals? Can you count how many carbons you have and figure out the chemical shifts in the environment? We don't even worry about the splitting. So here, could you see that you have 1, 2, 3, 4 unique carbons? So you should have 4 spectra. And so here's 1, 2, 3, 4. 4 spectra peaks. Could you see that this is your carbonyl because it's up here? And then the rest of these are lower filled. Now the one below here is the coupling's turned off. And you see how it's kind of neater? And most people do that because the coupling doesn't really help you too much on carbon. These are different types of carbon, so don't worry about those. These are kind of more my favorite here, though. I like these because they show you if you have an even number, it goes negative. If you have odd, it does positive. So there's some neat little spectra that you can do with carbon. Interpreting carbon, like I said, I like this one better, right? It's just easier than all the, you have this carbonyl here at 175, and then you're going to have this carbon will be the next one, that's at 70, and then you're going to have these other 3 here, 1, 2, 3, in the alkane region. Magnetic resonance imaging, MRI, this is basically what we use as a non-invasive diagnostic tool for seeing our ligaments. It's the same thing as NMR. We just didn't want to scare the public. So this is an MRI scan of a human brain. Think about it. You have a lot of hydrogens in your organic material. And this is a pelvic area of the NMR. So that should wrap up just what I expect you to know for NMR, and hopefully you can work your problems, and then you can work a few quiz questions and a few exam questions on solving some spectra. I don't consider giving probably more than 5 spectroscopy questions on exam 1.